We're in your chemistry book. We're in chapter 10, section 2, and it's on oxygen. Section 1 we just finished was on hydrogen. We find that hydrogen was the most plentiful of the universe. And now we have oxygen is by far the most abundant element in the Earth's crust. And in fact, most of our rocks have oxygen in them, and our sand has a silicon dioxide is 50% oxygen. And 21% of the volume of our atmosphere is free oxygen. Can you believe that 2/3 of our body, our human body, is made of oxygen? And 90% of the mass of the Earth's oceans are made of oxygen, of course, with H2O being made of oxygen. All our vital biological molecules, 1/4 of the atoms, of the living atoms, are made of oxygen. And oxygen is essential in metabolism of our bodies. So here we have a lot about oxygen. It's essential in metabolism. The element oxygen, it actually exists in 2 forms. That's pretty important. O2, as you see here, O2 and O3. O2 is by far the most plentiful, and these are allotropes. And what is an allotrope? Allotropes are forms of the same element that differ in their properties but exist in the same physical state. And so we have oxygen and oxygen, but O2 and O3 are quite different because ozone is not very stable chemically as oxygen, regular oxygen, and they come in these 2 forms, O with a 2 and O3. Just remember, those are the 2 allotropes, and these have a different physical state altogether. Ozone is very different than oxygen. So onto their properties, and we're talking about properties of oxygen. Oxygen is odorless, tasteless, and colorless. Its melting point is negative 218 degrees centigrade, and its boiling point is also negative 183 degrees centigrade. That's why oxygen in a normal state is in a gas. So both the liquid and the solid states are blue. So when you think of oxygen, of course, you think of it being blue, right? Basically here, coloring oxygen blue. So the preparation of oxygen. Well, oxygen basically is prepared commercially by distilling liquid air. So you take the liquid air or filtering this air, and you get 20 million tons a year of oxygen. So 20 million tons a year is quite a lot of oxygen that is made through the commercially distilling liquid air. Oxygen in the Earth's atmosphere is replenished by the process of photosynthesis. You know about photosynthesis. It's the process in which plants use energy from the sunlight to convert carbon dioxide and water into oxygen and glucose. So we should know all about that, especially if we're studying plants. Photosynthesis is a picture here of photosynthesis, and here is the equation, which you should kind of know what photosynthesis. Basically, taking in the plants, here we have a leaf here of a plant, taking in this sunlight, and the light going in all the light reactions here, and going in the producing glucose from the sunlight, and taking in carbon dioxide, that we breathe out carbon dioxide, and the plant takes in this carbon dioxide needed for processing glucose, which makes the plant, brings the plant in. In fact, we can eat a plant because it's sweet and has glucose in it. So we have glucose, and then taking in water, so it needs carbon dioxide and water, and needs these 3 things, 1, 2, 3, and then it puts out oxygen that we breathe. So photosynthesis is important in our lives. If we didn't have plants, we wouldn't have enough oxygen in the air. Photosynthesis. So here's the production of photosynthesis, the equation here. I think it's important that you kind of know about that. The equation And they basically, you need 6 carbon dioxide right here and 6 of molecules of water, 6 to 6. And then you have light, and the light comes in to process it. And then you get glucose and oxygen, right? And glucose being here 6 molecules of carbon and hydrogen and oxygen. This is glucose, 6, 12, 6. So this is what glucose is right here. 6 here. You can count them. 1, 2, 3, 4, 5, 6. Right here, glucose. And then 6 of oxygen. So the reason you need 6 is because the glucose requires 6 of each of these to produce the molecule of glucose. Okay. So photosynthesis, very important. Plants produce 10 to the 10th metric tons, or 10 to the 13th, basically here, of carbon into carbohydrates. That's a lot of tons there. With the byproduct being of 10 times, or 3 times 10 to the 10th, with 10 zeros after, of tons, metric tons of oxygen. So we need oxygen, and the plants provide. So we got to keep those plants around, huh? Excuse me. Small amounts of oxygen be produced in the laboratory. So in the laboratory, what happens here? A lot of times they use in this in the laboratory, sodium peroxide is used, but in this laboratory one, it's not sodium peroxide, it's potassium. So here we have potassium chloride, to which small amount of manganese is used here as a catalyst. So we have potassium chloride, and then this here, chloride. This is potassium chloride, and it is made into, with this catalyst of magnesium, or manganese, I should say, into potassium chloride and oxygen. It's another way that oxygen can be taken out in a laboratory. So here's a picture of it set up for laboratory preparation of oxygen. Here we have in the test tube some potassium chlorate. Chlorate means there's oxygen in there too. So that's where the oxygen is. So we want to get that oxygen out. And so it goes through, goes on the oxygen here with the laboratory burning, goes through here, and is through the oxygen is produced and displaces the water here, and the oxygen is up here at the top, comes out of the water. So it's a way of with the catalyst being manganese. So anyway, so let's go on. Hopefully I can. There we go. So. And these are an alternate method is, of course, instead of using potassium with the K, you can always use sodium, and that's where I got sodium. So sodium is the symbol Na. So mixing the sodium with water instead of the potassium with water, and then we'll get oxygen again. The same procedure, only you're using sodium instead of potassium. Sodium and potassium are both, in the metal, or the alkaline metal group, or basically they're in the same group number 1. Oxygen may also be produced by electrolysis of water. That means putting electricity through the water, and they pass a spark, and this discharge produces ozone. Wow. So we have 3 oxygen, O2, with that electricity. This actually happens in the air too, and it produces 2O3, which is ozone, but it needs to be heated at a high temperature, at that time, or plus, not high temperature, 284.5 kilojoules of temperature, I should say. So the positive H indicates that the reaction is endothermic. The product has more energy and less stable than the reactant. So basically, the product is less stable in that way. And then with producing the ozone, you'll smell a sharp odor, and you'll detect this at this high voltage. It kind of smells like electric trains, ozone does. Or after an electrical storm is due to ozone. So basically making ozone from oxygen with this electrical discharge basically puts off this you know, the energy at that point, to that point where it smells like a electrical reaction. So here's with steel wool and burning in oxygen. When I think of oxygen, it actually causes burning in many cases too. So oxygenation may ignite. A lot of time fires need to ignite because a fire needs oxygen. So oxygen is moderately reactive. It forms with all elements except for helium, neon, argon, and krypton, which are our most stable, noble gases. So, but oxygen combines with almost everything. If we take the periodic table here, let's go through it. I don't know if you can see this well here. Let's see where oxygen is. It's not clear on the right side. You see right here is oxygen. You'll see, let me go up here so you can see. Basically, you'll see the atomic number being 8 here, and atomic weight, oxygen here. It's going to be on this edge and underneath. So oxygen and sulfur are similar, so you'll see that. So anyway, I wanted to show you where the table, but it can unite about virtually everything except for the noble gases. These gases here at the end are called noble gases because they do not react very easily at all. And especially they don't react with oxygen, helium and neon, argon, krypton. We'll learn about those later. So let's put that back. But everything, if you look on the periodic table, you can get an idea about every single of these elements. So on oxides, we have normal oxides. Let's see, and they are. Here we go, normal oxides having 2 ions, peroxides having O2 with 2 negative ions, and superoxides having O2 with 1 negative. So they can be an ion with 2 negative electrons, or you can have 2 oxygens with 2 negative, or this. So these are called normal oxides, peroxides, and superoxides. So those are kind of important to know too. Whereas lithium forms with oxide, the more reactive metals, we've got lithium, we have sodium, potassium, and onto Rb and Cs in that, which is rubidium and calcium. All of these on your, let's look on this table again where they're at. They're in this first column here. All of these react with oxygen, of course. And in reacting with oxygen, they produce peroxides or superoxide when they unite. Here's some examples here. It's kind of like we need to know here too, because you probably have, these are exactly the same in many ways because of where they're at, the lithium and the sodium and the potassium. So, but here we have, as they're reacting, you'll see whether they're reacting. See, here we have lithium, 4 lithium and oxygen, 2 lithium, oxygen. This is a normal oxide. And then here we'll have with sodium, a sodium peroxide reaction, which is a little differently. And then we'll have potassium superoxide. So you can see this. And it depends on how many ions they have to do this. And Rb and Cs in that group, rubidium and cesium actually react the same as potassium reacts here with the superoxide. Just see how it's unusual, all the different ways that oxygen can combine. So it's good to know. Combustion is burning, right? And it's very familiar involving oxygen. A lot of things are burned because they have oxygen, right? Hydrocarbons, as those in gasoline, burn atmospheric oxygen to produce carbon dioxide and water. So here's the equation here at the top here to know. Here we have this equation, and see if I have written that one down. this octane. For the, for example, octane, one component of gasoline. You can see here how it goes down. They use 25 oxygen to ignite it, and as the octane is ignited, you'll see it puts off 16 of carbon dioxide and water. So when you're burning, what we have, carbon dioxide and water. Methane reacts the same way. In the midst of, here we have methane. This is the molecule of methane gas to oxygen producing carbon dioxide and water. So carbon dioxide and water. Same thing that we produce, really. You know, as we take in with our oxygen, we breathe out carbon dioxide and give off water, don't we? Acetylene, the same way here in the torch. It produces a very hot flame at 2,400 degrees centigrade in a welding iron and steel. And here you have the acetylene torch and oxygen producing, again, what do they produce? Carbon dioxide and water. All of these molecules break down into the atoms and end up producing carbon dioxide and water. So that's the way of gasoline. So as we important to know, they all three take all these different molecules and they're breaking down with oxygen into carbon dioxide and water. Same as we give off carbon dioxide and water too. Just remember that. It's kind of uses. Now let's just see what oxygen is used for. I have a list of it, so you can read it here. I'll just go over the list here. Here's a picture of the medical use of oxygen. This baby receiving oxygen, right? So the uses, oxygen is the most important industrial chemical in the United States. It's used for industries. Billions of pounds are sold of oxygen. One for manufacturing steel. We need to manufacture steel, you need oxygen. It's used in the hospital. It's also used for divers. When they basically dive in the ocean, they're going to have to use oxygen. It's used for the astronauts to go into space. They need oxygen. The synthesis of chemicals need oxygen. As we saw, the chemicals burning with the gasoline, they need oxygen. Oxygen torches for welding, liquid rocket fuel for oxygen, all these things. It's used in the metabolism of life. For us to break down our carbohydrates and such as breaking down, we need oxygen or we would not be able to do this, right? A human adult uses 500 liters of oxygen per day. So 500 liters of oxygen per day. So, and going on to the ozone. Okay, let's go. The ozone can deodorize air. What is ozone? What is ozone? It's sometimes used in place of chlorine in purifying drinking water. Remember, to purify your water, you usually put in chlorine tablets to purify the swimming pool, get rid of some of the bacteria and such. You're going to put in chlorine. Well, sometimes they use ozone to purify, but ozone is a lot more expensive. But sometimes to purify drinking water, you can use oxygen, which is ozone. And ozone is different because it has O3, right, instead of O2. So, and ozones can also deodorize the air and deodorize sewage. It also can bleach textiles and such. So let's go on to the next. Oh, this is an important article to read. I'm just going to kind of go over it kind of quickly here, but it's the ozone layer controversy. Have you ever heard? This is about the environment, and people were worried about the ozone layer. And if we started destroying the ozone layer, we'd get in a lot of UV light that will come in and basically causing more cancer and causing, in the long run, possibly killing the environment, right? So we have the ozone layer, which is the upper stratosphere, clear up above the oxygen of our air. And there's a layer called the ozone layer. And this layer keeps out the ultraviolet rays that want to come in. and they're bombarding these rays. But the ozone actually protects from some of these ultraviolet rays from coming through. So there's types of ultraviolet rays, as we can see. We have UVA, UVB, and UVC. Just think of ultraviolet A, ultraviolet B, and ultraviolet C. And so the rays of C are strongly absorbed by the molecules of the atmosphere. The C rays don't get in. They're actually the strongest rays too. And ozone protects us from those strong ultraviolet rays coming in. And excuse me. So here we have oxygen gas with the UV rays actually at this point. The atomic oxygen produced can either combine with another oxygen to form O2 or with the O2 molecule to form ozones. So when it does form, these two form oxygen 3, it's very much stronger in producing and absorbing the ultraviolet wavelengths. So important here. So ozone O3 absorbs the lower UV lights of ultraviolet B2. So a lot of the B lights do not come in. And then basically here we have ozone. Here's how they do with the UVB lights here, and absorbing them, puts out oxygen and O plus heat. So that's what happens with with the ozone. And then it may form ozone later. It helps protect the inhabitants of the Earth's surface from excess ultraviolet exposure to the sun, right? So all of the UVC lights are absorbed and some of the UV lights, but basically some of the UVA lights, ultraviolet lights can come through. So let's go, okay? I'm gonna go down here, which talks about a little bit about the ozone layer. Because ozone is constantly being produced in the upper stratosphere of the UVC protection in it, and it's called the ozone layer. The concentration of ozone is actually quite small, but if all the ozone normally presented latitudes were squashed into a single layer of ozone, the layer would be only 3 millimeters thick. Nevertheless, this layer is sufficient to block most of the UVB rays and C rays that reach the atmosphere. Well, let's talk about in the 1970s, what happened in the 1970s. Some scientists and environments began to argue that a man's activities were damaging the ozone. What we were doing, we were damaging they were arguing about the ozone layer through nitrogen fertilizers that were being produced, airplanes and automobiles too, also thought were damaging the ozone in 1970s. But the main thing as we go up here, and here is chlorofluorocarbons, CFCs. So you'll hear about this when the environmentalists are talking. They're going to be talking about CFCs. This has to be chlorine, chlorofluorocarbons. And in these fluorocarbons, they were basically causing problems in the ozone. And where do these fluorocarbons come from? From refrigeration. Freon 12 is one. And also, basically, not only that, but also through other types of chlorine type molecules. So for example would be the Freon 12 here that diffuses into the upper atmosphere with our refrigeration. What happened basically, you see here's the Freon and how basically it is from the UV light is separated into CCIF and chlorine. So now we have a highly reactive chlorine atom. Chlorine reactive then will definitely react with ozone because it's highly reactive. And so here we have a picture of it, how it's reacting with the ozone and causing the ozone to be depleted. So we have chlorine reacting with ozone, O3, producing chlorine oxide and onto regular oxygen and coming down, and actually is decomposing the ozone layer. So, and that's what they're afraid of. This whole equation is with the environment. It's like, oh no, we're going to have the ozone layer depleted, and we're not going to be able to be protected of ultraviolet light. So this would deplete the amount of ozone present, and the chlorine atom is regenerated in the second step again. So here we have a picture there. Chlorine is quickly taken out of circulation by other reactants though. Because chlorine is so reactive that it will not only react with oxygen, but it can react with nitrogen too that's in the air. So basically the chlorine is going to react with about everything. So that way, possibly would save the ozone layer. So this was the hypothesis now was that this worldwide would phase out spray cans. Basically, CFCs were in refrigeration, but they were also in all of our spray cans of everything. And so they were saying, do not buy any hairsprays or anything that's sprayed from a can that have CFCs in it with chlorine. Basically, they're saying we're outlawing chlorine. So in 1970, this started happening. The fears of this ozone depletion were revived then in the 1980s, and they were saying that ozone over Antarctica was suddenly dropping in the spring, probably due, they felt, to all of our CFCs. You know, all of these CFCs, what CFC again stand for is chlorofluorocarbons, chlorine fluorocarbons. And they basically wanting to get rid of those so that we wouldn't have a problem with the ozone layer. So going on, they said basically by the polar vortex and all this, and you can kind of read here of Antarctica, they were worried basically to say that we need to take chlorine out and allowing this chlorine to react with the ozone with the sunlight here. And here's a picture of how the reaction happened with ice to deteriorate. And basically then finding that actually this happened in Antarctica quite often through history. So it wasn't the CFCs necessarily causing this. So the response was then that the British Prime Minister Margaret Thatcher and Ronald Reagan got onto this Montreal Protocol. Basically in 1992 then, George H.W. Bush thought there should be a ban on CFCs. By the year 2000, he thought we should ban all CFCs. So they were going to ban refrigerants, they were going to ban industrial solvents, agricultural fumigants, firefighting chemicals. All these things have chlorine in it and CFCs in it. So, but now we find out after closely evaluating everything that was going on, we find something else out. You know, basically there's supposed to be this big ozone hole in Antarctica, and it was claimed later on that it was widely exaggerated. This global disaster was predicted, and it was going to happen in the 10% in the next 100 years or whatever. This ozone was, we were going to have this huge problem with ultraviolet lights, and now we find that this ozone hole did not follow as predicted. So the CFC crusade to ban all man-made chlorine compounds was to bring industrialization to its knees. Industry would be affected terribly if we took away from chlorines. And this Montreal Protocol really presented a lot of hysteria and exaggeration and hasty conclusions. But we are responsible to be good stewards, as God says in the Bible, right? And not to be careless, but we need to also have common sense, I should say, in the midst, and not focus on the hysteria of this whole subject. And it came to pass now that it hasn't deteriorated the ozone hole as we thought that it would do. So So that was pretty important. The last little section here has to do with hydrogen peroxide. And hydrogen peroxide is, the formula is H2O2. So, of course, H2O is water, but you put some oxygen, another oxygen bind, and you have hydrogen peroxide. And it's colorless and syrupy liquid. In the pure form, melting point is negative 0.9 degrees centigrade. It's used for hydrogen peroxide. It's used for mild antiseptics. Basically, you can clean out a wound to get rid of bacteria with hydrogen peroxide. It's also used concentrated for bleaches. It bleaches things out, textiles, fur, and hair bleach. It's used for rocket fuel sometimes. And they usually put hydrogen peroxide in brown bottles. Why do you think they put it in brown bottles? I find that they put it in brown bottles because it reacts to light. So it doesn't reach to decompose it if the light would decompose peroxide. When you pour peroxide, it kind of foams a bit in a cut or scrape, but that's because it's releasing that oxygen. So the foaming causes, and basically this here, where you have two hydrogen peroxides here, and it turns into water and oxygen. So that foaming coming out when you dump hydrogen peroxide on a wound, and you see all of a sudden, ooh, it starts stinging a little bit, and then you see the foaming is because oxygen is being released out of the peroxide, and this foaming thing. So this antibiotic action is due to these free radicals, they call, and these free radicals cause irreversible damage to bacterial cells. So this whole thing has been an oxygen, kind of a longer one, because oxygen is so important. So let's look at some of these questions really quick here. Sand is an oxide of a what element? Silicon. Silicon oxygen is silicon dioxide. Is 50% in sand. Now you can read that up. What is an allotrope? Is the form of the same element in a different physical state, like ozone and oxygen are allotropes. They're just in a different state. So how is oxygen most often prepared commercially? By distilling liquid air or filtering the air molecule commercially, sieving it and put it through a sieve, So what is photosynthesis? It's a process where plants manufacture glucose, and in manufacturing glucose, they put off oxygen, and give the equation. So we looked at that equation. You got sunlight activating carbon dioxide and water, and onto producing glucose and oxygen. Remember that, and you can look back on what that is, that equation of photosynthesis. Pretty important. How could you prepare oxygen in the laboratory? By decomposing potassium, using potassium or sodium, the thermal decomposition of potassium chloride, you can make oxygen, or sodium chloride, you make oxygen. How could you prepare differentiate between oxide, peroxide, and superoxide? So we kind of went over that in detail, and you could look back on there. Peroxide is O2, or oxide is O2 with two negatives. Basically, peroxide is O2, two negatives. This is basically O2 with just two ions, and then on to superoxide. So you can look that back up. I have to write that down. Write a balanced equation of the combustion of butane. So you can look back at that here. It's basically the one that's actually in. Let's see if I can put it here. I don't know if you can read this here, but let's put it. Here's the combustion of butane right here. I'm not going to go over that whole thing, but so you can see how combustion of butane with oxygen and how it produces carbon dioxide and water. So got that. So list 5 uses of oxygen. Oh, of course, manufacturing steel, used in the hospitals, divers need it, welding torches, rocket fuel. So and ozone. What's ozone? is purifying drinking water and deodorizing the air, and also prevents UV light, right? Give the formula for peroxide and list two uses. Right up here we have peroxide. Right here is the formula, H2O2, right? And it's a foaming antiseptic and a bleach. Also used to bleach textiles, all these things in the midst of peroxide. And so, which is sometimes they call it hydrogen peroxide, right? Write the equation showing the decomposition of hydrogen peroxide. Here we go. Here's the equation. 2H2O2 goes water and oxygen in the balanced equation. So that's it for oxygen.